How are you doing on like filling out the rest of the data structure? Give me a thumbs up if you got to your percent copper 2 sulfate in the hydrate. Give me a thumbs up because I don't know where you are. Alright, so maybe we should just chat for a second before you, if you're good to go, you keep on trucking. But for those of you who are a little stuck, let's just process a little bit of the data together. So what is the piece of information you gleaned from the two pieces of information you gleaned from the simulation? Cole, give me one piece that you got from the simulation. Okay, so you got the initial mass of copper 2 sulfate, and it says blank hydrate. Okay, so that's the total, right? All right, what's another piece that you got, Ryan? Okay, so the final mass gave us what? This whole thing again? No, check again. Look at the simulator. Because you guys saw it went from blue to what? White, right? So it was showing a chemical change. It showed the copper 2 sulfate, blah, 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 hydrate that was blue. And then you heated it, and what happened? It turns white. Can you tell what happened, why it turned white? Okay, now it says plus what? Plus water, right? So we pulled the water out. We dehydrated the sample. It was blue with the hydrated in the hydrated form, and we made it anhydrous. So we pulled the water out by evaporation. So this is just copper 2 sulfate, no hydrate. So I'm going to put without water just so you're clear. And your mass would change from initial to final, right? Well, what do you think that change represents? The what? The loss of water. So that difference in mass initial and then the mass of the copper 2 sulfate, that mathematical difference is the mass of the water. So then, therefore, you should have grams of water that you can establish. From there, you guys can convert to moles, like it says, like what's the molar mass in the data table. You guys can convert to moles in each of those substances and then proceed. Help each other out a little bit. The one that I'm speaking of. So it says percent copper 2 sulfate, right? Then, but this is all based off the data. You're not pulling this from the correct table anymore. You're pulling it from this data. So what data have you collected about copper sulfate? No, that was the hydrate one, or just the copper sulfate. The final mass, right? Okay, so then how about figure out from that sample you had initially, how about figure out percent copper sulfate without the initial sample? Guys, Ariane's good. Because when is the final represent? All right, Ariane, speak up for me. How are you getting percent copper 2 sulfate? So one of the pieces that some of us are struggling on is how do I get this? Help me out here.
You put the final mass on top because it's just
Okay, so the final mass is just representative of the compounds, just copper 2 sulfate.
Yeah.
And you'll
put it over the initial mass, which is all.
Shh, I'm trying to help you guys out a little bit, okay? Thank you. The initial mass, because the initial mass was collectively what?
The whole hydrate.
The whole hydrate. And then what would I do to get percent here?
You divide it in times the something.
There you go. All right, so that's going to be how you guys get percent copper 2 sulfate, and then you can also do the same thing for water. Keep processing for another minute. Give me a, how many 6-6 are in your measurement? 4? I would have 4. Because you're giving better data. Yeah.
So the mass of it will be the initial mass.
Because that's your loss of water. It's all different data. Yeah.
Oh, I think you know. No, I
Once you get to your percents, I'd like for you to compare that across your groups, because though we all have different data, we all should have similar percents. Though we all have different data, we all should have similar percents. The math. And then initial minus. Yeah, initial minus final. Yeah. All right, take 30 more seconds wherever you are, and let's talk briefly where we are in the process, because you can't quite finish without me. Not quite.
Where'd you get from?
All right, CJ's table. Okay, so guys, back to me. Halfway shut your computer, so I know you're with me. You can kind of still keep it, but you're holding on to it for a moment. All right, so CJ table, can you guys tell me what you guys decided on the percent copper 2 sulfate? Around 64%. Give me a thumbs up. Hand raise something that you got close to that. Looks like collectively we were able to get mostly there. So that's the percent copper 2 sulfate. Now, everybody, what should be the percent water, knowing that percents add up to 100? What should that be? Who got that mathematically? Awesome. So we have some consensus here. So this is a compound, right? It's going to have an established amount of copper 2 sulfate and an established amount of water for it to be like a given compound. So the reason we wanted to relate this to moles is because there is a relationship. It's mass and moles, because this is percent by mass and this is moles, and they definitely have a relationship. So what was your number of moles of copper 2 sulfate? Somebody at CJ's table? No, actually I need just one person, because everybody's moles were slightly different. CJ. 10 to the negative 4, that was moles of copper 2 sulfate. Okay. What was your moles of water? 0.00413. Okay, now, no one else got this data, because everybody's data was different, right? Yes? Okay, so though we don't have the same exact number of moles of each of these, we should still have the same ratio present between the copper 2 sulfate and the moles of water. So here's what we need to look at. Which of these is the bigger number? Water or copper 2 sulfate? Water, right? So that's like 4 times 10 to the negative third. That's 8 times 10 to the negative fourth. This is the bigger number. So whatever is your bigger number, I want you to take the bigger number and divide it by the smaller number. Whatever your bigger number of moles is, take that and divide it by the smaller number of moles. Make sure you put parentheses, because you know your calculator's not as smart as you want it to be. And CJ, I'm going to keep using your data, because, you know, I'm using your data. Great, CJ, can you tell me that ratio? 5.2. All right, can I get some more ratios? So when you take your big number divided by your small number, Hannah?
4.9.
4.9, Bailey? 5.0, somebody else, Benoff? 5.0, more? I got more people. Estes? Okay, Jacob? Almost?
5.3.
5.3. All right, so maybe can we make a consensus on what the integer ratio is between water and copper 2 sulfate? About what? About 5. So I have in this compound, I have 5 times as much water. Or I didn't want to say that. As much what? Say again? Hydrate, which is water, right? So I have 5 times as much water as I have copper 2 sulfate, mass-wise and moles-wise, because they are related. So 5 times as much water. So that's essentially telling me a ratio. I have 5 waters for every how many copper 2 sulfates? 1. So it's a 5-to-1 ratio. So for every 1 mole of copper 2 sulfate, I should have 5 moles of water. And that's always this consistent ratio within copper 2 sulfate. So what I would then write, you guys see where I am on the worksheet? Like towards the middle, bottom. So what I should write here is, since I have 5 times as much water, I have a 1 to 5 mole ratio. I'm going to have 1 copper 2 sulfate for every 5 waters. Therefore, I would name this as what? Name it for me.
Copper 2 sulfate.
Copper 2 sulfate. Go ahead.
Pentahydrate.
Penta. Where are you getting penta from? The 5, right. All right, so, sorry, smartboard doesn't always work sometimes. So that's what we are working on today a little bit more. We're learning how masses and percents can kind of pull down to some ratios, which we call empirical formulas and molecular formulas. Okay, so I want to give you an intro through what we've had already started, and then it's once you get the process down, the steps down, it's really easy, and we're going to finish those up today in class. Okay, will you guys pull up your lecture notes from last week that I provided you, the sheet? And shut your computer so it just saves battery. We're not going to be on that one for a little while, okay? So pull out your lecture notes. If you didn't quite finish this, you will have time hopefully to finish this at the end of class. So read and write down what you need to from the board. If you're looking for this information on your notes, you will not find it exactly there. I've mainly provided you the problems that we'll be doing, so you don't have to do the problems. So this is your beginning of your empirical and molecular formula. I'm almost done looking over your problem sets. I'm going to review number 4. Maybe a couple of others too. So we've actually been dealing with empirical formulas this entire week, or last week. We've taken all of our compounds, our ionic compounds, and we have made them their simplest ratio, or their smallest whole number ratio. So whenever I mention simplest ratio, what do you maybe think of when we are looking at ionic stuff? What do we always do with our subscripts? We always crisscross charges, right? So that was like how we got new subscripts. But what if I had something that was a 2+, like calcium is a 2+? I'm going to start down here. And I had oxide, which was a 2-. What do I get when I crisscross, guys? Well, hold on. First off, what do I get when I crisscross? CH2, O2. But you're like, Enlo says we can't leave it like that because what can we do? We can simplify. We can reduce. So you guys would leave that as what for me? CaO. So basically, you reduced to the simplest ratio. So what you've been writing for all of our ionic compounds, every single time you've literally been writing the empirical formula. You just didn't know you were. So, and a couple of you guys asked me like, oh, if I have let's see here, diphosphorus tetraoxide, what would that be? P2O4. Like, did we reduce this? Anything covalent, did we reduce them? No, we never did, because this was literally the formula of phosphorus or diphosphorus tetroxide. That's the compound's molecular formula. So we never reduced the covalents because I never asked for you to, because we would never, ever, ever reduce anything covalent unless I suggested the empirical version of the empirical formula. So this is called a molecular formula, which we're going to get into at the bottom down here. It's the true formula. So if I did take a molecular or a covalent compound and I said what's empirical, you would reduce all the subscripts down to the simplest way we could. So this hydrogen peroxide, how can I reduce that? HO, right? Well, we write no H, but yeah. So that would be the better answer for this, right? Okay, for glucose, C6H12O6, what would be the simplest ratio? CH2O. So you're saying C1H2O1, because what did you do for each of these subscripts? Divided by 6 all the way through, right? So that's 6 divided by 6, which is 1, 12 divided by 6, which is 2, and 6 divided by 6, which is 1. So we're just simplifying these ratios. It's pretty simple. So with molecular, that's called the empirical formula. I'll call this EF from now on. The molecular formula is legitimately what the compound is made of. It's like exactly what it's made of. There's no reducing. It's the truest formula that exists. And we will call that the molecular formula, MF. So give me a thumbs up when you get the main points down. So would you guys consider this a molecular formula or an empirical formula? Molecular, because it can be simplified, so it's not in a simplified version right now at all. All right, so call out to me here. Empirical or molecular? So basically, you're telling me, is it in the simplest form, yay or nay? Why? Because you can't simplify 1 anymore, right? There's H1, so that cannot be simplified. So this would be considered the empirical formula. It actually might be a molecular formula as well, but it's the simplest formula, so we would call it empirical. Next one? Why molecular? You can divide them all by what? 11, right? So that's definitely written currently as the molecular formula. Next? Because it's got a 1 in it, right? So it's already simplified as far as it can go. Next? Good, and you should recognize this as what? As, what's the name of this? Calcium sulfate, right? Because it was a calcium with a 2+ charge. Sulfate had a what? 2-. So when we crisscross charges, what do? We reduce. So we wrote the empirical formula. And then we're going to hold off on this one because mercury's weird. Okay, this is the guts of today. Basically like the how-to, the steps it takes to make this happen. I'm going to write this down in a simplified manner on the whiteboard over there, but I want you to see each step for the full nature you could really describe it as. So this is like your answer. This is your answer key in disguise. This is how you will do stuff. All right, so write down steps to calculate EF. I know my light is out up here, so it's harder to see here. I'm just going to call this out loud. Okay, so step 1. Convert amounts of all substances to moles. Simplify that for me, Chris. Give me like 2 words. That's 3 words. I'm going to say get moles. There you go. Get moles. If I give you grams, how do you get to moles, Bailey? Right, if I give you particles, how do you get to moles, Ryan? Right, if I give you liters, how do you get to moles, Munir? If I give you liters, how do you get to moles? 22.4, right. So whatever I give you, you get to moles. That's your goal, right? Step 2, To get the simplest ratio, divide all moles by the smallest moles. Simplify that for me in your screen. I'm just going to say divide by smallest moles. Okay? Of course, you can get specific. I'm leaving that there for you. I'm just simplifying. And then step 3. If these numbers are roundable, round to the nearest whole number and make them the subscripts of the formula. If these numbers are roundable, round to the nearest whole number and make those subscripts, make those numbers the subscripts of the formula. So I'm going to simplify this. Round and then subscript. So you're rounding the number you just got in part 2, and you're making it the subscript. And that, my friends, is the compound formula. That's the empirical formula. So here's the rules on rounding. They're kind of tricky, so I want to use those as an example as we go through today. If you have something that is 0.85 and up or 0.15 and down, you can round it to the closest number. So if it's like 2.15, what would I round that to? The 2. If it was 3.85, what would I round it to? 4. So that's what I'm talking about up here. But if you get like 2.5 or 1.5, you're not going to round that because that would be skewing our moles too much. So we would multiply everything by 2, and that's everything. Not just the number that's the 0.5. You would multiply everything by that integer. So I'm going to give you guys a second to see this, write down to me for rounding rules. So we may not see all of these rounding situations today, but I want you to have that as a reference if you need it on your problem set. I'm going to scoot you ahead, get your last piece you need. Alright, so we're going to do an example first with the empirical formula. So since we're just so full of knowledge, we actually know how to identify percents, we should be able to interpret percents. We're going to start with that to be our main example. So, do we have a conversion from percents to moles? Think about our mole map. Yay or nay? Is percent on our mole map? No, right? But everything we've been messing with percent so far has been mass percent, so it's like mass of the thing we want over mass total times 100. So there kind of is a relationship between percent. There definitely is a relationship between percent and mass. So what we do is anytime I give you a percent, screw the percent, ignore the percent, call it out of 100 grams. Then we're like, yeah, I can deal with grams. How do I get from grams to moles? Molar mass, right? So that's such a natural thing for us now. We're going to use the thing that comes natural. So if I give you a percent, assume a 100 gram sample, and then take that percent and call it grams. So I'm going to do 1B first for you. So if I have a percent, I'm like, nope, can't work with percents. I'm going to do what? Assume a 100 gram sample. So if I have a 100 gram sample and I have 79.8% carbon, how much carbon do I have? 79.8 grams of carbon, right? And then how much hydrogen do I have? 20.2 grams of hydrogen. So write down this example as percent. Maybe note to yourself, you assume a 100 gram sample, and then this is how we're starting. Now it's a piece of cake. So what's the process for converting these grams of carbon to moles? What goes on top? Everybody should be able to tell me here. 1 mole of carbon. Okay, and then what should go on bottom? You need a periodic table, unless you just memorize these. Thank you. 12.01 grams of carbon. Okay, so go ahead and get that number for me. You guys have a calculator, so if you don't have one, go grab one now. I should probably find my calculator. Yeah. Yep, so grams of carbon and grams of carbon cancel. All right, Camilla's table, can you guys give me your moles?
6.64.
All right, I'm good with rounding a little bit here because we don't want like 18 decimals all the time. All right, so Chandler's table, tell me how you would process the second part of this data. We're starting off with 20.2 grams. What do I need to do? So what do we do on this first one? Grams where? On bottom. So I'm squeezing mine in here. So there's grams of hydrogen. Okay, so grams of hydrogen. What's the molar mass of hydrogen? Here on table. 1.01, and that's related to what on top? 1 mole of hydrogen. Good. All right, so I think we can do that basically in our head. 20.2 divided by 1.01 is about what? It's about 20 moles of hydrogen. Okay, on our simplified steps here, boom, boom, boom. Which one have we done? We've done get moles, right? So now what do I need to do now? Divide by smallest mole. So who's smallest moles here? Carbon, right? So divide 6.64 divided by 6.64, what's that? 1, right? That one's easy. It's the same number. And what's 20 divided by 6.64? You have to give me approximate. Like, what is it? 3.01? Is that what you said? Yeah. 3.01. Is that roundable? 3.01. Is that roundable? Yeah. Totally. It's super close to what? 3. So I'm going to put 3 here and circle it so I know that I've rounded that 3.01 down to 3. Okay, so we've taken the moles, we divided by the smallest moles, and then we get that integer that I've circled, the 1 and the 3, we've rounded, and those are now the what? Subscripts. So the formula for this is C1H3, or just CH3. And that's your empirical formula. You just take the numbers, you call them subscripts, you move on. You guys okay? All right, so we know our 3 steps at this point. Let's do this again. But I started you off with the percent one just so you could see how I could skew the way I presented data to you. But it's just really easy. Just take that percent, call it grams, and move on. Now, this would be like at a crime scene. They found a 120-gram sample of some white powder. They analyzed it, and it contains hydrogen and carbon. And here's the mass of carbon they found. And they want to know what the substance made of. They want to know what it's consisting of. So we have a 120-gram sample, and we have 96 grams of it is carbon. Which of those pieces is really the most important one right now? The what? 96 grams of carbon. So write down 96 grams carbon. What's the rest of the sample made of, Maverick? Say again? Well, read this question with me. If we have 96 grams of carbon, how much of it is hydrogen? You guys can do that at your table if you wish. I'm just trying to get one person at a time here. Sorry, don't give me, I don't know 1%, because basically if I already had a percent, I would have had to go to grams. If you bring me back to percents, I'm going to go back to grams. I'm in a big circle. So if I have a 120 gram sample, 96 grams of its carbon, and the rest of its hydrogen, how much hydrogen do I have? $24 grams, right? And here we go. You guys work the process. Boom, boom, boom. It's just I was presented in a word problem in this one, so I'm easy one. Very simple.
Oh, yeah.
If you feel good, check yourself, and then move on to number 2, which is on the board still. So I'm expecting that I'm sorry that this is kind of my way or the highway, because it's the right way or the wrong way. You have to put units. You have to show the process of converting to moles. You have to show the process of dividing by the smallest moles. You can't just say I did it in the calculator. So this is a way to, like, a fail-safe way to get you on the right path. You don't always have to show me canceling units, but it's nice for you to know that you canceled your units so that you know you've achieved the correct answer and things like that. So I'm not like being super obnoxious about the detail. I'm just trying to show you the right way to so you have a path to success. All right, Aiden, get me started on number 2. What are you going to process here?
Well, you have to convert to moles.
Okay, what am I starting with?
You're starting with 0.858. 0.321 grams of fluorine.
So this is 321 grams of fluorine, and this is a total sample, right? So what else do I have?
That's 0.537.
I believe you. I hope. 7. Yeah. Okay. And this is grams of what?
Grams of copper.
Good. Okay. Let's see here. My knowledge table. Can you guys tell me after we get this data, what would you do next? Okay, what's the molar mass of fluorine? 19, gotcha. I'm going to ask one table at a time. 19 grams of fluorine, and that's converted to 1 mole of fluorine. All right, Nana, what's the molar mass for copper? 63.55 grams of copper, and I'm putting this on bottom so I can cancel. All right, how many moles is this, Estes?
0.0168.
Moles of fluorine,
Yeah.
right? Wesley, can you tell me the copper moles? 845 moles of copper. All right, what would I do next? Munir's table, once I get to moles? 5. Who? Right, so divide both of these, 5.00845, 00845. Everybody's, what's the copper one? 1, okay. Bryce, what's the first one up here? 2.1. Probably nothing else. Okay. So we look here, we're like, okay, that's easily 1. This is going to be what? 2. So I'm going to round that up to 2, or down to 2. So what is the empirical formula, guys? CuF2, right? We don't put, so if you put like F2Cu, that just looks ugly. You probably identify like, oh, there's a metal and a non-metal here. What do I always have? What's the order I always have to list them in? Metal, then non-metal, right? So that's not correct. It'll be CuF2. And let's go ahead and name that baby. Write it down. Before you say it out loud, write down the name. All right, Corbin, what's the name? Good. And so we recognize that our transition metals need a Roman numeral. All right, close your eyes. Say the first step for empirical. Get moles. Okay, second step. Good, divide by smallest moles, and then round, and that number is the subscript. Okay, that's what you need to know. Okay, we're going to add on to this a little bit with molecular. Can I move on?
Yeah.
Okay, I got 3 people said yeah. Do they speak for all of us?
Yeah.
Yes, okay. So, to write down molecular information, which you'll notice that this is the key part. Do everything the same as EF, except we're going to add on this last piece of information. So this is how to get the molecular formula. not the empirical formula. So if you remember from the first time we had mentioned this a couple months ago, the molecular formula is just a multiple of the empirical formula. So like glucose C6H12O6, that's a multiple of the empirical formula CH2O. And so the multiple aspect comes in just by us taking some subscripts, multiplying them by the multiple. But how does one get the multiple? That's kind of the piece that we have to process in a word problem. It would be given to you as like molecular weight or molecular formula mass. And so that would be what we would call the compound mass, or the mass of the compound. The way it would be phrased in the word problem, though, is either molecular mass or formula mass, something like that. So it might say, oh, the formula mass or the molecular mass is 180 grams, okay, or 180 grams per mole, maybe more specifically. And then at this point, you're like, okay, what do I do with that? Well, you will have already possibly had the empirical formula from calculation, or be given that in the actual format of the problem. And let's say your empirical formula only weighed 60 grams per mole. So you would take the 180, you would divide it by the 60 grams per mole. You guys can do that in your head. What is that? 3. So the multiple between the EF and the MF is 3. 180 divided by 60 is 3. So all I would do is take the EF formula, let's say it's CH2O, okay, and I will multiply it by 3, bring that in and distribute. What would my molecular formula be? C3H6O3. And therefore, I'm done. I have the molecular formula. It's just get that multiple and then apply it. Can I move on? So I'm going to show you an example where we go through the easy part and then the hard part. All right, so notice in this one, it tells us the empirical formula. The empirical formula is C2H4S. Write down the empirical formula. And what do you guys think this is? That is not N. The upper part, so that's the mass of the compound. This is the mass, the molecular formula mass, right? So that's the whole shebang. Sorry. Okay. And at that point, we're like, oh, okay, what do I got to do? Divide it by what? Well, I don't know that yet, so what should I do first? Figure that out, right? So to get the molecular formula, I have to get N. I have to do EF times N. So to get N, I have to do the molecular mass, or also in this case it's called molar mass, divided by the EF mass. Well, this is 179 grams per mole. What's this one? 24, 28. 60, approximately. What is it? 60.13. So that's 60.13. So we take 179 divided by 60. Give me an approximate here. 3. What is that exactly, though? What is that exactly? 2.98. So that certainly can be rounded up to 3. All right. So what's the significance of this 3, guys? It's in, right? The multiplier. So then we're going to take this, call that 3. So that would be C2H4S with a multiple of 3, which would give us what formula? 12S3. And so this would be called the molecular formula. Given this data, and we process it, we get this molecular formula. So molecular formula is pretty easy if you already have the what? You already have the empirical formula. But what if you don't have the empirical formula? What do you have to do? Find it, and then... Yes. So is that what you guys said you want to do now?
Yeah.
Yeah. All right, start with 3. Work at your table, talk it out. Write your information down.
So sick. Okay.
Point.
Wait, I got you.
Yeah, it's really.
I divided point zero
For
zero
the,
nine.
for the point 141,
I got
I got 0.0036. I got 0.0035. So
It says, it says it's 1.5.
maybe I did wrong.
Yeah. Do you guys round too much? Somebody round too much?
Because they're like the same number.
Uh-huh.
Yeah, we go much.
Hold on. I'm catching up with you.
Oh yes, it would round. It would round up. Yes, so it would be.
It depends on how much you round.
0.016.
Alright, you should be at the same point as I am at least. Give me a thumbs up if you got these moles for potassium. So I did use scientific notation, but you guys can figure that one. Potassium, sulfur, and oxygen. Okay, so don't forget oxygen is a component of the whole, so you're taking 0.4 grams, subtract the potassium, subtract the sulfur, the rest is oxygen, so that's how we got 0.144. All right, so you guys tell me what's your next step? Divide by who? So we have 0.00358, 0.0036 blah, and then 0.009. Who's the smallest? Who's the smallest? Sulfur, definitely sulfur still. 3587 times 10 to the negative third, and it's going to be relatively close on this top one, but you're still going to do it. So this one's definitely 1. What's the top one? Well, what is, give me exact. We can't.
0.002.
Okay, so 1 point, I got 0.005, but we're going to round that definitely down to 1. So what do we get on the bottom one?
2.51.
So I'm thinking around 2.5, right? Because a lot of you guys, if you rounded too much early on, you would have a problem. But if you kept out a couple of decimals, you should be fine. So this is 2.5, right? Can we round this?
Yeah. You multiply by 2, you get 0.5.
Right. So how do I just multiply? Do I multiply this one by 2?
No, you have to multiply all of
Them all. All right. So the ratio right now, and this is the right ratio. It's 1 to 1 to 2.5. But we can't put 2.5 as a subscript, right? So we can't skew the ratio. We have to keep the ratio the same. So that's why we're multiplying them all by 2, and then that top one by 2. So this is what? 5. This is 2, and the top one is 2 as well. So what is the EF? What is the EF? K2, S2, O5. All right, so now we have the EF. Now we're good. We can work through this. So this front table was on the struggle bus, but guys, they made it through, so we're good here. All right, so the experimental molar mass is 859.00 grams per mole. What is the molecular formula? So keep rolling here, okay? Hold up your number for N on your fingers. Ooh, I see some of us are saying 4. I see somebody saying 8. We okay? Number N. So we take the molar mass, which was a huge number, almost 900 grams per mole. We divide it by the K2S2O5, which added up to be about 222. You got this number down here. It's just an addition. So when you divide, you don't get 4, right? You get 3.86. But what are we allowed to do with that? Round it up to 4. And that is N. That's your multiplier. So then what is my new and improved multiplier? I mean, yeah. K8S8. Okay, whew, I'm done. This is some drug on the street they found. We don't know the name of it. I'm not going to have you name it. Some crazy CSI scene thing. Okay, who feels okay with the EF? Empirical formula. Molecular formula. All right, I have one more example for you to put to me. Look on your lecture notes. I have 10 example questions, but I don't think you need 10. I think that's a little overkill. You guys agree with me? Okay, I'm going to narrow down to a couple. Okay, so circle. You know, I'm going to go for the most challenging ones because why not? You guys can be challenged with this. You'll be fine. So it's 5 on the first set of 1 through 5. So I'm giving you percents. What do we assume? Okay, you're good. I've heard it. And then the last set, you'll do. Go ahead and start with 5. Start there. I gotta be picky here. Let's just do both 5s. Yeah, let's do both 5s. I cut it down to 20% of what I was going to do. I want you to impress me. Something to impress me. Yeah, I got you.